All right, electric power is like opening a floodgate on an appliance. Now, if you remember, we talked about power when we went outside and did the power step lab. Remember that? You found your power? And that it was work divided by time. Power was a speed. And so when we're talking about electric power, we're talking about how much electricity is going to plow through an appliance. And that appliance is going to then convert that electricity that it's eating and turn it into something else, like a lawnmower, an electric lawnmower. We're going to stick with electricity. Turn it into mowing. Turn a blender into blending. Some sort of motion or some sort of light or something. And so the power of the appliance, so power has to do with the appliance. Not so much the battery and the wires, but the appliance, the thing that's plugged in, the light bulb on the circuit. That's the power, and we're going to give that item, that appliance, a rating, the power rating, which we're not a stranger to this word, watts. We found your watts out of the power steps. We found that your power rating. Electricity has its own formula. We did work over time to find power, but for electricity, it has its own formula to arrive at the same number. It'll get you the same number, but it uses things more friendly to electricity. So you take the voltage, which if it's plugged into a wall would be 120. If it's plugged into a 9-volt battery, that'd be a 9. So you take the voltage. If its dad has a power drill, he's got this nice power drill, it has 18V on it. Wow, that's 18 volts, that's good. But for Father's Day, you saw also one that said 12 volt, 12V. Okay, it's not going to have as much power. So you know, and if you want Dad to have a ton of power for his drilling, then you get him one with a cord. And then that will have, this number will be 120 then. But now he's got a cord. So, and then the current. The current is what can go through that drill, or whatever it is, that light bulb, but the wires. So you have the push, and then the wires that can handle that push. You multiply those two, and that's the power. And you're opening up the floodgates. On your hair dryer, you have settings where where the fan blows soft or the fan blows gentle. What you're doing is it's the same voltage because it's plugged into the same wall. So it's the same voltage either way, but you're allowing more current through it. You're using more wires, and so you're getting more current through it, and so you're going to have more power out of your hairdryer because you've upped the current by engaging a new set of wires. Or there's another switch to change the temperature from off to medium to high. So then the heater part, the heating element on the hairdryer, it's the same voltage coming out of the wall, 120, that's staying the same. But you're allowing more current to go through the heating element then. So the whole hairdryer, when you have all the settings cranked real high, you have a higher powered hair dryer. You're allowing electricity to flood through it faster. That's why I picture these floodgates here. You're opening up the floodgates. So when you turn a device on, boom, you're allowing current to travel through it. How much current goes through it depends on the wires that you have and the volts that the source that you're plugged into. You multiply those two together, and that's your power rating. And you can get different powered light bulbs, different powered garbage disposals, different powered, we did hair dryers, ceiling fans. As you click the chain thing into different settings, you're changing the power rating. This number is pretty fixed because we're not asking the power company to make changes. We're changing the amount of current that goes through by engaging more wires or fewer wires. So you can do all sorts of, just plug numbers in. They do P for watts, P for power, that makes sense. V for volts, that makes sense. They do I for current, that doesn't make sense to me. I think I could probably have it make sense in my brain, but it's not worth the time. But A must already be used, and C is already the speed of light. So they sit there and go, okay, all right, so they use an I for current. I'm not going to get all hung up on those details. Besides, your tests are going to be all the quizzes multiple choice anyway on this stuff. So, but P for power. All right. And you just plug the numbers in it's basic algebra. Easy peasy. You can do the study guide ones. You can do these ones. And the question would look like this. A 60-watt bulb. Boom. You put that in the left side, the power number. And you plug it into 120 volts. What's the amps? And then you solve it. You could, if it was a regular school year, I'd have you be doing the calculating laws, calculating power assignment there. I'll probably have you skip it. But it ends up being a division after you set it into your algebra problem. And this one, you have 120 volts that goes into the volt spot. And it's a 1200 watt hair dryer, so that's your power number. And then it ends up at 10 amps. That won't pop a 15 amp fuse. It won't pop a 15 amp fuse. But if you use 2 hair dryers, each one will pull 10 amps through this one, 10 amps through that one. It'll be 20 amps. That'll melt a 15 amp fuse. So don't invite all your friends over, during the quarantine especially. But don't invite all your friends over and then have everybody bring a hair dryer and then plug it all in to your bathroom all at the same time and turn them all on. Each one is going to open up floodgates, floodgates, floodgates. Each hair dryer will be okay, but the wire feeding all of them, the wires to your house, will become overloaded with all the current trying to get to the pot of gold on the other end. $1 billion flow around, and it's going to overheat. When you turn on your hair dryer, sometimes the other lights go dimmer because so much electricity says, oh, I'm going to go through the hair dryer instead. Hair dryers use a lot of electricity. They're high powered. Energy, we've talked about energy. Energy is the ability to do work at the universe, right? Energy, you got matter and energy. We're going to focus more specifically on the electrical nature of energy, when energy is electricity. Energy can be the other 5 forms as well. But energy as electricity, wearing the mask of electricity, the way you calculate is you take the power of the appliance and how long you had it on. The power of the light bulb, how many watts? The power of the light bulb, and then you times it by how long the light bulb was on. So I had it on for 1 hour, 2 hours, 3 hours. And this time is in hours, and this would be in watts, except they actually make it kilowatts, 1,000 watts. So, and the unit for energy, normally it's joules, but for electricity they call it kilowatt hours. You could turn one into the other. But since this is kilowatts and this is hours and they're times, they just say kilowatt hours. It's not kilowatts per hour. It's not kilowatts per hour because, correct, it's not divided. Per hour would be power over time, which would get us some other unit we can figure out, I suppose. But it's power times time, so it's not per hour, kilowatts per hour, it's kilowatt hours. Your power bill, do I have a sample power bill here? Your power bill is all on kWh's all over the place, and they charge you per kilowatt hour. So if you use, 1,000, let's say 400 kilowatt hours, and they charge you 10 cents, 15 cents, 20 cents, whatever it is, per kilowatt hour. You can look at it if you're truly interested. You'll get your bill one day. If you want to do these problems, I have the work shown here for you. But basically, you just take the numbers from the problem, you plug them in. Which of these is a unit of power and which is a unit of energy? A watt measures power. Kilowatt measures power. Kilowatt hour measures energy. All right. Transformers. All right. What a transformer does, this is a transformer here. You see them in older parts of towns. Older towns, they got the big barrels up on the power cords. This is a transformer that you can buy for your car. They come in different looks. I have one. It doesn't look like this, but I have one that is like this. This is a transformer on this. I have this one on the side of my house for my solar lights. Not my solar lights, that would be dumb. For my LED lights, landscape lights. And this is a transformer. What do these transformers do? They massage the electricity into more voltage or less voltage. Sometimes we want more voltage, sometimes we want less. So this one, LED lights don't want 120 volts. They only want 12. My house is 120 volts though. So how am I going to massage electricity to 12 volts? You buy a device. It steps down the voltage. This steps down the voltage before it gets to your house. And they have these on the streets as well, too. So you don't want to open them up, otherwise you get electrocuted. This one steps up the voltage. So your car is a 12 volt is battery, and the alternator, it's all 12 volts. But if you want your computer plugged into your car, your computer needs more than 12 volts. You need to up the push of electricity. this device, you plug in your cigarette lighter, which is 12 volts, and then it juices it up to 110 probably, or close to 120 at least. How does it do it? By looping wire. We talked about loops before. We don't have to get into the exact how, but by inside of each of these, they loop it with more loops on one side than on the other, and then that will up the current, up the voltage. You lose something though. You lose current. As you gain voltage, you lose current. You don't just get extra voltage for free. So if I plug this into my car, all my wires I'm going to be spending more money on electricity as I try to get extra voltage. I will have to feed this guy lots of current. My wires won't be happy with me, and I'll have to put my gasoline. I'll use more gasoline to do it all, but I can at least use a computer at the same time. So that's what a transformer is. It adjusts the voltage. It can increase or decrease the voltage, and there's step up and step down ones. You'll read about that in the book. And then batteries. We're nearing the end, folks. Batteries. Batteries are a device that converts chemical energy into electrical energy. You put chemicals in here, it's kind of all built into the paste with metals and acids, and then the acids dissolve the metals. And then as that happens, you end up with positive ions in one spot and negative ions in another, and it's a chemical reaction. Positives over here, negatives over there. That's your difference. That's your voltage. And then when you connect the two, there'll be a flow. And as they flow, the chemical reaction keeps going on, and so you can continually have a charge flowing. It doesn't just do one zap and be done, because there's more chemicals that will keep replacing the ones that just left. So that's what a battery does. And I used to think that batteries were pretty much, just Duracell batteries, and that was basically all there was. But now that people are doing electric cars and electric houses, and we want all these smart devices and phones that last longer and computers that last longer and so forth and so on, everybody wants to now have a better battery. So they have a whole battery for your house. So that's all happening these days. So batteries are not just some sort of archaic thing that we've learned in the past and we don't need to improve. People are trying to make better batteries, more powerful batteries. Why don't people want to buy electric cars? Why aren't electric cars big? Because batteries are weak. They would love to make a battery-powered pickup truck that could tow a boat. They can't, because batteries are too weak. But maybe one day they'll find chemical reactions strong enough to create a charge enough to shove that motor hard up a mountain pulling a boat. But at the moment, batteries, they're getting better, but they're not as wow as people would necessarily want them to be. And then once the metal rods and the chemicals are all spent, then the battery is dead. And a rechargeable battery rebuilds those chemicals. Not as perfectly as they originally were. And now we'll head into towards the end of the school year here, and we're going to look at how that format's going to be, and I'll explain that more later. But as far as the notes are concerned, we're done, people. Here's the beautiful thing. I want you to appreciate this. You guys made it through the entire book. You got through the entire thing. Normally, teachers, they just get through the first half of the book or this or that. We got through the whole thing. We learned exactly how the whole universe works. Just think about what thing in nature didn't we talk about? We talked about lightning. We talked about chemicals. We talked about stars. We talked about gravity and things falling and colliding. We talked about it all. And you guys were right there with us. So I really want to say you guys did a great job this year, and I know you had a lot of curveballs thrown at you with all the different things, with just situational changes going on in this world. But we got through this, and you understand this world. You can always go deeper into any of these things. Of course you can. But we touched on every single one, so that at least the conversation could start. And you can open up a book, and it's speaking a language you understand. So great job. Great job. And I hope that this science stuff, this nature stuff, resonated with you this year. All right, I'll talk to you later. Time for me to sign off.